Pra cantar samba, não preciso de razão, pois a razão está sempre com dois lados. Amor é tema tão falado, mas ninguém seguiu nem cumpriu a grande.
Now to your view, what do you think the lesson should be? What lesson do you take from Gödel's work?
Okay, so let's go back to the first Gödel theorem. The standard way of putting this is something like, given a theory of arithmetic which is sufficiently strong, that's a technical term, it's incomplete. So there are going to be things you can't prove or refute. That's not quite what the proof of the theorem shows in all the versions of the proof. What it shows is that it's either incomplete or it's inconsistent. Okay. Now, given that people like Hilbert and his program were working in classical logic, inconsistency implies triviality. If you can prove any contradiction, you can prove anything. And that renders the whole system pretty useless, okay? So the inconsistency horn of the inconsistency possibility was justifiably ignored. Now, Hilbert and company knew nothing about power-consistent logic because the invention of that's 30, 40, 50 years later. But we now know that there are power-consistent logics which you can use as the underlying logic of a theory, which is inconsistent, but you can't prove everything. It's non-trivial in the jargon. So go back to the proper phrasing of Gödel's first incompleteness theory. If you've got an arithmetic theory of sufficient power, it's either inconsistent or incomplete. Now, given the resource of power-consistent logic, we now have the possibility of taking the other horn seriously. So maybe arithmetic is not incomplete, it's inconsistent, okay? So you can axiomatize it. It's just that in doing so, you're going to get some inconsistency. And that's given rise to quite a lot of work in inconsistent arithmetic in the last 20 years. We now know a lot of what inconsistent arithmetics look like. Many of them are axiomatizable. And you can arrange for them to be able to prove everything that's true in the standard model. Now, let me explain what that means because people might not know this. So if you look at an axiom system for arithmetic, it has a kind of standard interpretation where you interpret the quantifiers as ranging over numbers. You interpret this sign as meaning addition. You interpret this sign as meaning multiplication and so on. So this is not just sort of symbols on a page. They have a standard meaning. You can think of it like that. And most people think there's a standard interpretation of this language of arithmetic. And this is a model in logicians' terms. It's an abstract structure. And you can, the truth in the standard model would normally be taken to be the things which are really true about numbers, okay? What the first Gödel result shows, at least in the traditional interpretation, is that the things which are true in the standard model are not going to be recursively enumerable. So any consistent axiomatization is going to just give you a part of that, okay? So what the work on inconsistent arithmetic has shown is that you can have inconsistent arithmetics which actually establish everything that it holds in the standard model. Of course, you can establish more.
Yeah.
The thing is inconsistent, but the inconsistent.
Like, for example, the Gödel sentence, would that turn out to be?
That would turn out, depending how you do it, that is likely to turn out to be both provable and its negation is going to be provable too. Mm-hmm. It's going to be a sort of paradox, which is sort of what you expect initially when you look at the Gödel proof.
Yeah.
So you can, in these arithmetics, prove everything true in the standard model. But that's not recursively enumerable. It's another one of these cases where a recursively enumerable set can have a non-recursively enumerable subset. Okay. So you can prove everything that's true in the standard model, and then you can prove some other stuff too, like, sort of things like the paradoxes of Gödel's undecidable sentence, and other junk too. I mean, there are lots of technical issues here, and I don't think this is the place to go into them. But
what does a model of inconsistent arithmetics look like? I mean, how does it differ from the standard model of classical arithmetics?
Well, there are many. Look, even in classical logic, arithmetic, even the set of things true in the standard model has many models.
Mm-hmm.
One is standard and the others are non-standard, and they have an interesting structure. Once you move to a paraconsistent setting, you've got all those non-standard models and loads more, okay? And what really distinguishes the paraconsistent structures
so you have chains, for example.
Yeah, the most commonly studied class of models have loops. So you go through the numbers, maybe you go past all the standard numbers into the infinite numbers. Okay, so they're non-standard, but sooner or later you go round in a loop.
Okay.
Those are the most commonly studied forms of inconsistent models.
Yeah, remember you talking about that in Brasilia.
Yeah.
So you do have a first like something exactly like the standard model, and then you have loops.
It's more complicated than that. But some of the non-standard models will be like that. Some of them are actually finite. Okay, so you go up to 37 and then you loop round.
Okay.
Right? So there's a rich variety of models of inconsistent arithmetic. What really is doing all the hard work though, when you examine what's going on, is this. When you axiomatize arithmetic, you do so with only one predicate, okay, which is the identity predicate, x is y.
Okay.
It's the only predicate that you get in standard axiomatization of arithmetic. So if the theory is inconsistent, there have got to be inconsistencies involving the identity predicate.
Not the greater than and lesser than relation.
No, because you define all those things in terms of the identity predicate and the arithmetic function symbols.
Okay. How do you get the asymmetry
Of what?
Of the greater than and lesser than relations out of identity? Or is it?
Because you define x is greater than y, just if there is some z that you, okay. X is greater than, let's do the other way around just to get the lexicographic ordering right. X has y greater just if you can add some z to x to get y. So there's no symmetry there because it's z you've got to add to x, not y. Okay.
I see.
So you can get away with just one predicate, okay, identity. So if the theory is inconsistent, there must be inconsistencies involving that predicate. And so the identity predicate must behave inconsistently. So predicates in paraconsistent logic have extensions, things which they're true of, and anti-extensions are things they're false of. And so in these logics, the extension and the anti-extension of the identity predicate are going to overlap. So, crudely, there are going to be some things of the form A is B, which are both true and false in the model.
And this kind of thing might be precisely something like x is greater than y and y is greater than x. Is that the kind of inconsistency that you might bump into?
If you have looping, you're going to get that kind of thing.
Yeah.
Of course, you can't have, if x is greater than y, let's stick to the same ordering. If y is greater than x, okay, then you can prove that's the case in arithmetic. 37 is greater than 5. So that's always going to be true because you've got everything true in the standard model.
Yeah.
But you can arrange for things, you can arrange for a contradiction to say that it's not less than it too.
Yeah.
So, you know, you may have models in which things can be less than and not less than each other. That can happen.
Are there any known applications of that, for that matter? I mean, what happens to the standard application of arithmetics for counting or for doing things in physics?
Well, that's an interesting philosophical question. Prima facie, nothing can go wrong, because after all, you can prove everything true in the standard model. So anything you want is there. Okay, so prima facie, everything's going to work out fine. The worry is going to arise because you might be able to prove too much. And then the question is, well, what is this too much? What inconsistencies can you prove? And how might they screw things up, say, in practice? Okay, that's a very interesting question. A first answer is that if you play your cards right, things won't get screwed up for the following reason. When we apply arithmetic, we apply it to physics, economics, biology, and we're dealing with systems which are pretty finite. Okay. Certainly mathematicians and mathematical physicists quantify overall numbers, but no one's ever made use of the number 10 to the 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 10, because it's bigger than anything that there is in the cosmos, all right? So really, really large numbers don't seem to play a very essential role in physics or other branches of applied mathematics. So if you choose your inconsistent arithmetic such that it's all consistent up to 10 to the 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 10, and the inconsistency only happens after that, then it's not going to affect your physics.
Yeah.
Okay. So I think you can argue about that.
It only affects it in potentially, let's say. So the possibility of unwanted results is there, but no actual unwanted results.
Yeah, as long as you're dealing with things which are finite, and the inconsistencies only arise when you get to the numbers which are beyond that level of finitude, then you're okay. That's an interesting argument. It's arguable, it's debatable, but I find it kind of plausible.
Okay, well, thank you very much.